right, welcome everyone to the last chapter in chapter 4, or last part, I guess, last lesson, talking about combinations and probabilities. So this is leeching off of our previous lesson, which was talking about the counting principle and permutations. So let's get right into it, shall we? Here are the objectives for today. So we're going to continue on from last time, kind of with combinations. So we're going to first compute the number of combinations of n individuals taking k at a time. And then we'll use everything we learned about these counting principles, combinations, permutations, all that stuff, to calculate probabilities. And so this is going to be a little dense on the other side. Okay, combinations themselves, not super difficult, but we'll think about the concept behind each of these, and that's really where this is going to be kind of a challenge. So stay tuned, take out your notes, and let's get started. All right, last time we did the permutations and counting principle, which helps us to count the number of arrangements or outcomes, okay, and specifically when order matters. So today we're going to talk about the other concept in this group, combinations. So you've probably heard of these before if you've heard of the other two, okay, but we're going to look at what makes this a little different from the other two and how it helps us find or count the cases that we need. So let's get to the definition. The definition of a combination, it's a selection of individuals from some group in which the order doesn't matter. So if there are n individuals that you have and you want to choose k slots to fill, then the notation nck represents the number of different combinations of k individuals chosen from the entire group of n. So let's break it down. First, you may want to really notice and really highlight in your notes, the selection doesn't matter. The order of selection doesn't matter. And this is the main difference between permutation and combination. Okay, they look almost identical, but the only difference is that combinations just simply do not care about the order of your objects, where permutations definitely take that into account a little bit more. Let's see some examples, okay, of these things in action. And from last time, we only knew permutations, so some of those examples might even fall under the combination category. So here are the two categories I have for examples. I got order definitely matters. So as far as your interpretation goes, these are pretty non-arguably order matters. Okay, picking student body representatives, for example, student president, student vice president, student treasurer, secretary, whatever you want to say. Okay, the order in which you fill those spots matters because each like slot has a different job. That's one where order will definitely matter. Another example would be your order in baseball, since if you bat first, typically you aren't really subject to a board of outs or a full bases loaded situation. Whereas if you're later in the order, you may have to face those situations that are different. And here are some examples where order may not matter. Okay, so last time I think I opened up a list of chores option. Okay, but typically this doesn't matter. If your mom asks you, or your dad, I guess, if your mom or parent asks you, okay, to do a list of chores in a given day, it doesn't really matter what order you get them done in, as long as you do the chores that are listed on your thing. Right? So that's one where it may not matter. Of course, depending on your situation, you may have to do one before the other. But that's why I said may not matter here. But combination could work to count that result. Another one which is pretty definitely doesn't really matter is rolling 5 dice in Yahtzee. I don't think anyone really cares if you've played Yahtzee before, whether the first dice is like a 1 versus a 6, but you're just looking for all of them to be a high roll, okay, or something you can get a winning hand with. All right. So those are two cases where order may not matter. So now what I'd like you to do real quick is just think of a combination scenario in which the order may not matter. And I'll be able to give you feedback on whether or not that is in fact a combination or a permutation. All right, so let's take a look at our factorials once more because we're going to need these to also calculate our combinations. Okay, so remember, a factorial is when you take a number n and you multiply it by every consecutive lower integer up until you hit 1. Okay, so that's our definition of factorial. Here's the combination formula. Okay, so essentially we're just taking the permutation with the same numbers but dividing it by a k at a time, a k factorial. Okay, so in other words, if you want to rewrite it without the p part, the final formula is the one right in there. that you see circled in purple. Wow, really bad circling job. I don't really know what's happening there. Let's try it again. There we go. That's better. Okay, so that's the formula you're looking for if you want to do combinations by hand. Of course, your calculator definitely has this NCK button, so I would suggest being able to use that to get where you want to be. All right, now let's take a look at some examples. So here's example 1. You wish to form a 3-card hand with a standard 52-card deck. How many different hands are possible if the order doesn't matter? Surely, if you've played a card game before, you may have get in your hand, and then you maybe shuffle the cards in your hand. If you play any other card game that's not just regular cards, you may be guilty of doing this so-called hand shuffle, where the cards in your hand get shuffled around because you like them in a particular order or something. But the truth is, the order of that hand doesn't really matter. You have the same cards no matter how you shuffle them. Okay, so let's take a look at this. Okay, if the order doesn't matter, I've got two numbers here. Okay, I've got two numbers here, 52 and 3. Okay, and in our 52, we can call this our n, and we want k to be our 3. Okay, that's how many things we're trying to fill. So when we take a look at the formula, we say this is 52 choose 3. Okay, or we could write it as 52 pick 3 divided by 3 factorial, okay, which is the same as saying 52 factorial over 3 factorial over 52 minus 3 factorial, which sounds like a lot of work. Okay, this is why I suggest the calculator can do the work for you. Okay, but really, you can simplify this even more to 52 factorial over 3 factorial times 49 factorial, where this 49 factorial will cancel with this to make 52 times 51 times 50, and you divide that result by 6. Okay, so let's take a look here. 52 times 51 times 50 over 6. And the result is about 22,100 different hands. Okay. So that's a lot smaller than the presumed permutation version of it, which there would be a lot more combinations. But this cuts out all the duplicate hands. Okay. All right, here's an example you can try. All right, there is a pizzeria near you, and you really like their pizza. Today they got a deal for you to pick a pizza with up to 5 different toppings, and they offer 20. How many different pizzas can you order? Now, I'm pretty sure if you ask anyone, the amount of toppings you pick and what order you pick them in doesn't really matter. They all get baked into the pizza in the end anyway. Okay, so take a look at this, try the combination formula out on it, and tell me what the answer is. All right, now that we've gotten through our combinations, a bit of that, okay, let's talk about putting it all together. So we're back to talking about probability. Okay. Now these last 3 techniques we've told you about, the counting principle, permutations, and combinations, are all ways of counting unique arrangements or outcomes in some situation. So you can use these techniques to find the outcome in a specific event, or the total outcome representing the entire sample space. Okay. Here's an example. Some seating arrangement questions. Imagine 5 chairs lined up with 10 people. Of the 10 people, 4 are girls and 6 are boys. We can ask several different questions regarding the chance of certain events occurring. So let's start with a prompt here. What's the chance that only boys sit in the chairs when the music stops? Well, first, we need to find how many ways this can be organized in the first place, okay? How many ways can it be organized? Now, when you're talking about boys versus girls here, order doesn't really matter, okay? So we have 10 chairs, okay, or not 10 chairs, sorry, 10 people and 5 chairs. So we have 5, 4, 3, 2, 1 as our chair slots, right? And we have 10, 9, 8, 7, 6 ways to fill them, all right? And that will basically tell us how many actual ways to organize there are. Okay, which if you do this, it's 10 times 9 times 8 times 7 times 6. And I'm going to erase the bottom here. We don't need these slots anymore, since they only helped us count the chairs. If you do this factorial here, or this like mini factorial, you should get 30,240. So there are 30,240 ways for this to line up. Okay. Next, we need to find the total event outcomes. Okay. So our event is boys in the chairs. Let me move my answer here up a little bit so you can actually still see it. There we go. So we need to find out the chance that only boys sit in the chairs. Okay. Now we only have 6 outcomes because the other 4 are girls, right? So 6 times 5 times 4 times 3 times 2. Okay. This will give you a total of 720 different arrangements. Now I think you know what's coming up next. We take our answer here, the event, okay, and divide it by the total number of outcomes in the system. I picked white instead, it should be red. So here we have 720. And we're going to put that over our total ways to actually pick this. 30,240. And we divide. 720 divided by 3420 is about 0.024, or 2.4% if you're following along with that. Does that make sense? Sure, there's only 6 boys. If you wanted to load them all up with 5 boys in the chairs, it's probably a low chance. Okay, so that's an idea here. Now note that I did not think of this as a order doesn't matter scenario, and if it did, you would actually have to, be careful about how this goes down, since some of these numbers might be repeat organizations of the others. Okay, which you'll be able to see what I mean by that, okay, in the homework and the practice. All right, and the last thing I want to mention here is that these 3 have a very strong correlation, relationship, okay, resemblance, whatever you want to call it, to the general multiplication rule we learned back in 4.5. Okay. In some cases, you can apply this general multiplication rule to determine the probability of certain events that would be otherwise using combinations or permutations. So let's take an example we've done before. Okay. The chance of 5-card hand being all spades. In the general rule of this, you may have remembered this from last time as 13 over 52, which is the chance to draw 1 spade, over 12 over 51, over 11 over 50, over 10 over 49, over 9, 48. Okay. If you remember that, this is going to also look similar to counting principle. Here's what that looks like. In the top, 13, pick 5, and on the bottom, 52, pick 5. So, just as a little review, please answer the following question. Okay, hopefully you got a bit out of that. The top refers to 5 cards being spades. So remember, our event space is limited to our 13 spade cards, okay? And I'm picking 5, and hopefully they're all spades. So that's why the top is represented with our permutation, counting principle, whatever you want to call it. Okay. We're using permutation in this scenario, but you can use any of the 3, counting principle or combination, to do the same work. Okay. And the bottom, we have the total cards in your hand, total combinations your hand could possibly be, including things like hearts, diamonds, clubs, all that other good stuff. And we are assuming order matters in this. If you want to get a little more, detailed, you could say that these are combinations instead, in which case it would change the idea of these numbers in order to cut out some of the duplicates. Okay. But that's the general idea when we're looking through this. So I hope you've been able to watch this video a little on the longer side. Please take breaks as you see fit. Come back to it later. We will talk about the IP and practice when we come back from iStep.